Improperly designed and built low water crossings block aquatic organism passage, such as shown in this picture. However, like other road stream crossings, such as culverts or bridges, low water crossings can also pose a risk to livestock and equipment and cause chronic water quality problems. Low water crossings can be built with many types of equipment commonly found on farms. Front-end loaders or a blade on a three-point hitch can easily be used to push material around and into place across a stream. However, unless a ford is placed at a site that offers natural stability and built according to a few design principles that work with instead of against the stream, it may not persist over time. So in general, low water crossings are built on low volume or unimproved roads on private lands. They're attractive because they're generally cost efficient and can be relatively easy to maintain. In addition, they can be designed and built to pass large sediment and debris loads with some efficiency. However, because they are a static structure in a dynamic system, they affect river mechanics and aquatic organism passage. So planning for passage on a given operation could be easily incorporated into our overall planning process. The nature and extent of a landowner's operations are key pieces of information needed to determine use and locations of crossings on a property. For example, an essential part of designing crossings involves knowing the types of equipment used on a farm and the number and kinds of livestock that might be using a crossing structure. The type of equipment used on a farm has a direct influence on the type and design of a low water crossing. We deal with a large range of different operations that use implements that vary in size, from big to small. In addition to considering the size of individual pieces of equipment, we also need to account for various other equipment and implements pulled by tractors and trucks. The physical dimensions, weight, turning requirements, and clearance of single vehicles and towing combinations are important factors that dictate crossing design requirements. Here are some common types and categories of low water crossings in use today. The top two consist of simple fords located at naturally stable features or fords at similar control sections improved with materials that harden the travel surface. The middle two are known as vented fords and consist of a hardened road surface underlain by corrugated metal or concrete box culverts, for example. The bottom structure is a low water bridge where the road surface is supported by piers or spread footings with a natural channel bottom, and the structure is meant to be overtopped by larger flow events. As you may imagine, these things range in cost, construction requirements, and their effects on stream and passage continuity. I showed a couple of vented fords in the previous slide, and one metric that describes the effect of a low water crossing on stream function is the vent to area ratio, or VAR. VAR is the ratio of the constructed openings of a crossing to the bankful area of a stream. Low VAR crossings are those where the area of the vents is much smaller than the bankful flow area of the stream. And high VAR crossings are those where the area of the vents is greater than or equal to the bankful flow area of the stream. So in general, fords, high VAR crossings, and low water bridges all support good river function and passage. Low VAR crossings and other structures that affect sedimentation, debris dynamics, these things impair passage in much the same way as a culvert does. They create sections with shallow depths, high velocities, or elevation drops. The magnitude of these barriers often scales with stream size and flow. Often, the more improved a crossing is, the bigger a barrier it creates, assuming, of course, that the crossing wasn't designed specifically using passage considerations. So here's a couple of examples of low VAR structures. These crossings in Illinois and Texas are both jump, depth, and velocity barriers to migratory aquatic organisms. Further, they basically operate as flowhead dams and force a slack water reach above the crossing that affects stream dynamics. By comparison, simple, unimproved, or improved fords, such as this one in northwest Arkansas, provide year-round passage and can remain stable for years. Granted, they won't support the same equipment load as the two crossings shown in the previous slide. But fords like this represent a good number of the crossings that NRCS installs. Simple fords offer a good mix of construction ease, stability, safety for livestock and equipment, and generally work well with the stream over time. All of this equates to good passage conditions, good stream function, and minimal maintenance. So low water crossing design and analysis should roughly follow the same procedures I've outlined for stream simulation culverts in years past. In fact, the low water crossing document I mentioned earlier suggests the use of stream simulation techniques for low water crossings at high VAR structures as well as improved fords. Consequently, it's best to characterize the nature of the reach as either transport or response and account for the flux of watershed materials. Generally, crossings tend to function best when they are designed and built to conform to existing channel geometry and slope, constructed to match the shape of the existing channel, and oriented to cross the stream at a 90-degree angle. So cross-sectional geometry has a big effect on the type of crossing structure that's appropriate, will provide safe and reliable access for livestock and equipment, and will persist over time with minimal maintenance. The concept of channel entrenchment is useful here because entrenched channels require different structures than a relatively unentrenched channel. Entrenched systems focus flow, sediment, and woody debris in a small area. Stream crossings have to account for these factors in the design process to maintain stability and passage quality. So this table highlights some of the major site factors that are usually attributable to larger watershed processes that influence the suitability of 4 general categories of crossing structures, which are shown above the top as column headings. The 4 general categories are taken from the previous slide that I showed: unimproved fords at naturally rocky sections, improved fords outfitted with material that hardens the travel surface, high VAR fords with metal or concrete box culverts, and low water bridges. The table highlights the applicability of structures at locations affected by common watershed or site factors. All 4 categories provide some measure of passage and stream continuity, some better than others, and each is better suited for certain sites affected by watershed factors, channel geometry, or flow regime. For example, unimproved and improved fords are better suited for sites with flashy stream flow or very low base flows because they usually minimize changes to a channel cross-section as compared to high VAR fords or low water bridges. Conversely, using an unimproved or improved ford is usually not advised in entrenched channels or broad channels that move a lot of water at base flow. So I'll go over some examples of unimproved and improved fords, vented fords, and low water bridges in the following slides. Rock fords, whether unimproved or improved by the addition of rock fill or other materials that harden the crossing and support equipment loads, are commonly used in the eastern U.S. As many of you know, one of the most important design considerations associated with this type of stream crossing is placement. The best mix of passage and stability conditions will be found when the crossing is sited at a naturally stable section of stream. Bedrock outcroppings, riffles, or steps composed of coarse material are great locations for crossings. If these sites are found within the landowner's property, we can go in and improve the approaches, add material to the stream adjacent to or on top of the naturally stable section, and use fencing and gates to control livestock access. Design and construction costs can generally be managed to small figures, and sometimes on-site equipment and materials can be used to complete the crossing. Improved fords are generally constructed by opening up the stream above or atop a natural control and backfilling the cut with a well-graded mix of rock back to the existing bed elevation. Sometimes it's necessary to augment or improve the natural control with larger material. Depending on sediment texture and composition, it may be necessary to line excavated sites with geotextile to control seepage or cut off subsurface flow that might flow under instead of on top of the backfill. When rock is added to a crossing to improve the travel surface, there's a danger of building a sediment surface that creates passage problems because of turbulence or depth and velocity problems. In addition, if rock backfill isn't well graded, water can flow through instead of on top of the travel surface. So the best conditions for improved fords are usually realized when the backfill is composed of a mixture that mimics bed material as evaluated from a reference reach adjacent to the crossing. preferably upstream and away from any influence of an existing crossing that might have made the crossing section different from a reference reach or a self-formed reach. A good rule of thumb for getting away from the influence of a stream crossing is to move upstream at least 20 bankful channel widths before analyzing channel geometry and bed material composition. Moving this far upstream helps you get away from any existing crossing effects that alter channel geometry or bed form composition and spacing. In addition, it helps get you outside of what might be considered as the crossing maintenance zone, where equipment operations have affected channel metrics. Developing a backfill mix that approximates the natural bed material requires a bit of characterization with respect to the stream bed. More data is usually better, but a backfill mixture composed of at least 3 to 4 particle sizes usually provides good bed stability and passage quality. There's an awful lot of substrate analysis methods out there. The one you use is likely going to be a function of familiarity, maybe regional calibration or ease of use. But whatever method you choose, I would suggest that it's important to account for bed shape and particle diversity. You might consider developing your own roughness information if extensive modeling will be used, and that also helps you to gain a bit of insight into stream bed mobility. In addition, it helps to note features that force bed morphology. An important example of this would be boulder force steps and mountain channels. It also helps to investigate any watershed factors that control permeability or that are maybe a function of site construction activities like compaction or excavation that may interfere with shallow groundwater flow. For example, each of these unvented improved fords in Oregon, Virginia, and North Carolina match the channel shape and slope, cross at a right angle, and the bed surface is composed of materials that closely match the natural bed forms. Consequently, they've been relatively long-lived and provide good passage across a range of flows. The backfill mixtures aren't complex and can be created at a quarry or borrow site so that trucks deliver a prescribed fill mixture for direct placement into the section. You can also stockpile each size class on site and create the backfill mix using construction equipment at the site. Buckets on loaders or excavators can be used for measuring out rough composition, as well as on-site mixing before placement into the stream crossing. So here's a shot of an excavated crossing being backfilled with rock layers composed of about 3 size classes. Once rock is dumped in layers, it can be difficult to mix the material so that the resulting stream bed surface is well graded. At sites where passage is a primary project purpose, it's usually better to mix the backfill at a quarry or staging area, place it into the cut, and blend it laterally to the road approaches and up and down stream bed forms. Rock size and gradation should be the smallest mix needed to remain stable under prevailing flow conditions. Bigger isn't necessarily better for passage because of turbulence and can also create problems for livestock. You may need to add sand or soil into the mix to seal the section to ensure that the stream doesn't percolate into the crossing substrate. In addition, smaller material increases bed diversity, chokes voids between bigger stones, and helps preserve passage quality. It's also important to extend the driving surface of the crossing to an elevation that exceeds the known high water level. This design element is a criterion in the stream crossing standard. Keeping the crossing at grade, providing surface roughness, and ensuring that the downstream edge doesn't produce a sharp drop in water surface is the best way to keep material and animals moving through a system. So cable concrete or articulating concrete block fords are a cost-effective means to improve a stream crossing in situations where traffic volume, average load sizes, or the energy regime might be higher. They're usually made of 1-foot square concrete blocks connected to each other with light cable. Block mats are usually available in pre-made sections in widths of 4 to 8 feet and lengths from 8 to 16 feet. The concrete blocks are usually between a couple and 8 inches thick. Some come with a geotextile backing already attached, but if not, a layer of geotex should be placed on the prepared subgrade before the blocks are placed. Scour protection around the mat area is important, and this can be accomplished by placing a single row of blocks at least 6 inches below the finished subgrade around the perimeter of the mat. Unless the subgrade is uniform, smooth, and well compacted, the blocks can shift over time. Each block is independent of its neighboring blocks and can settle, rotate, or tilt. If this occurs, it can result in damage to the mats and a rough driving surface that may be dangerous to livestock. Once the blocks start to move, scour can endanger the longevity of the crossing. So, subgrade preparation is a key element of crossing longevity for cable concrete fords. So here's a few shots of a crossing project in Oregon showing a cable concrete mat and excavator prior to installation. Juvenile Chinook moving upstream between the blocks the day after it was built, and the crossing after the first rain-induced high flow event in the fall. Voids between the blocks can be backfilled with smaller material following construction, but they tend to infill naturally in streams with relatively intact sediment transport regimes. Here's a shot of a cable concrete crossing on a relatively steep transport reach in Wyoming where the mat wasn't extended up the bank line as high as necessary. In addition, the subgrade at this crossing wasn't well compacted because of the presence of large boulders. Erosion and settling at the site has exposed some of the structural cables, which can be a hazard to passing vehicles. It's rough to drive across, but functional from a passage perspective. However, sites like this where the blocks have begun to move around often fail over time. Another form of improved ford involves the use of concrete as precast planks or reinforced poured-in-place slabs across the stream. They can be relatively simple, but also more expensive than articulated mats or rock-hardened fords. They're durable and well-suited for systems with flashy runoff and high debris loads. Concrete slab fords offer a very stable, smooth travel path, but if the surface of the slab gets covered in algae, they can be very slippery to livestock. A smooth concrete surface can also be a problem for passage, but if the crossing is fully submerged and set to match stream gradient, passage can be satisfactory. Sometimes low-flow passage slots are incorporated into slab fords, but these can be pretty hard to maintain and tend to fill up with bed load. Passage slots sometimes self-scour at higher flows, but problems generally arise during low flows when deposition in the slots blocks access and organisms are forced to try and negotiate the slab surface. Okay, here are a couple of examples of concrete slab fords. This crossing uses hog slats on an ephemeral stream where passage may be possible at high flows. Here's a poured-in-place slab crossing in Arkansas that was submerged at the time of the photo but has a small drop along the downstream edge that might present a problem for weak swimming fish or animals that crawl. Slab fords can be a problem for passage again when the crossing surface is wide and flows are shallow and fast. So it's important to do all you can to design these things to be underwater at all but the very lowest flows. Another way to improve a ford is to use geocells or plastic cellular confinement structures. This technology is best suited for low gradient streams with bed material consisting of sand and gravel. As with some of the other approaches I've talked about today, the subgrade for a geocell crossing should be smooth, uniform, and well compacted. This requirement, coupled with the need to properly expand and place the geocells before filling them, means that the crossing site should be completely dewatered prior to and during construction. Geocells should be placed on geotextile and then backfilled with a mixture of small gravel. Finally, the cells should be covered with a mix of larger gravel, and the top of the crossing should be kept to the level of the natural stream bed. Keeping a cover layer on the cells is important. Tire damage can weaken them and result in elevation changes that may affect sediment transport, crossing stability, and safety for livestock and equipment when uncovered geocells become part of the travel surface. Here's an example of a geocell crossing, and you can see the cells at various areas along the ford. Although not presently an issue for passage, the long-term stability of this crossing is a problem unless the geocells are covered with a surface layer. And I'd guess that a bit more excavation at this site would have helped preserve cover at the crossing, improving its function for farm operations and passage as well. All right, vented fords are found in many locations across the Midwest and eastern United States, and most were built between the 50s up to about the mid-80s. These fords commonly consist of multiple small culverts set at or near the stream bed level. that were covered with backfill and commonly capped with concrete or asphalt to harden the embankments along the upstream and downstream sides. Vented fords pass low flows through the pipes and are meant to be overtopped by high flows. Older vented fords typically have a low vent-to-area ratio and basically act like dams, causing upstream backwater and aggradation and sometimes downstream scour. Passage is often a problem because culvert outlets can be perched, and if not perched, often have high flow velocities. New approaches to vented fords that maximize the vent-area ratio offer much better passage and perform better across a range of flow, sediment transport, and debris regimes. High VAR fords can consist of bottomless arched culverts in smaller streams and multiple concrete box culverts countersunk and backfilled with streambed material in larger settings. So here's a couple of examples of vented fords. This is an older ford in Missouri that illustrates a commonly constructed low VAR crossing. Multiple culverts set at different elevations are capped by a concrete layer that extends along both margins of the crossing to armor it from overtopping flows. Passage conditions are suboptimal, and although one of the culverts is fully submerged, velocities are fairly high. This example from the Ouachita Mountains in Arkansas shows a new concrete box high VAR ford that maximizes the channel area across the section and is bedded with natural stream substrates. Both passage and stream continuity are largely preserved in a crossing like this. Another criterion under the stream crossing standard calls for the use of fencing and gates to manage livestock use of the area. As many of you know, it can be difficult to maintain fences that cross streams. Sometimes a fence that won't get torn up by high flow and debris doesn't do a good job of excluding livestock, and fences that handle livestock well are often great at catching debris. These shots illustrate a cross-fencing technique that I've used in the past on projects that seems to do a good job of handling stream debris and excluding cattle. Sections of 1.5 to 2 inch PVC are hung from a cable stretched across the channel, and turnbuckles at the cable ends help tension it when it becomes stretched or if the posts sag or move a bit. Each pipe section is separated from the next by rubber hose or smaller PVC slipped over the cable as spacers, and the pipes can be cut to various lengths to match the channel's shape. These things swing when pushed by high flow and even provide boat passage in larger rivers. Gates for livestock control are essential because, given time, cattle will figure these things out and push on through.